Spin is one of the most important properties of matter. Without it, atoms, magnets, and even part of the world around you will not work the way they do. The most disturbing thing is that spin is said to be a rotation, when in reality, it is not. Then, what the hell is this spin? To start simply, spin is a property of particles. An electron has a mass, an electric charge, and also a spin. A proton does too, and many other particles as well. That means spin is not some secondary detail, it is truly part of their deep identity. When a physicist describes a particle, they do not just say how much it weighs or what charge it carries, they also say what spin it has, because that changes the way it behaves in the world. The problem is that the word itself immediately creates a false image. In English, spin directly suggests the idea of rotating around oneself, like a top, a ball, or a planet. And naturally, your brain wants to picture a tiny sphere spinning very fast. That is normal, because our intuition works with everyday objects. But in the case of the quantum world, that image quickly becomes misleading. Spin is not an ordinary rotation that one could film with an ultra-powerful camera. It is not a tiny planet spinning in empty space. It is a quantum property, meaning something real, measurable, but not really resembling what your imagination expects. Simply because a particle is not a little marble. What makes spin even more confusing is that it cannot take just any value. In the ordinary world, many things vary continuously. You can walk at 1 km/h, 2, 2.5, 2.73, etc., etc. No precise set of value constrains you, but in the quantum world, some properties are quantized, meaning they can only take certain precise values. Spin is one of those properties. For the electron, for example, we do not say it spins a little, a lot, or enormously. We say that it has a well-defined spin. And when we measure its orientation in an experiment, we get discrete results, meaning precise outcomes. We do not get an infinity of shades in between. In reality, this detail is one of the first signs that spin belongs to a logic very different from that of ordinary objects. You can also keep in mind one essential idea. Spin is not something a particle creates by starting to rotate. It is something it has from the outset. I have already seen people make this mistake. An electron does not decide to acquire spin the way a wheel starts spinning when pushed. It comes with it. It is an intrinsic property, meaning it is built into its very nature. That changes a lot of things, because it means spin is not a visible motion that could be stopped or sped up like that of a toy. It is a fundamental characteristic of reality. I know I am insisting a lot, but this has to be firmly understood. At this stage, then, you should not try to see the spin the way you see an ordinary rotation. It is better first to accept it as a strange but indispensable property. A bit like accepting that a particle has an electric charge even though you cannot see that charge with the naked eye. We do not directly see spin, but we do see its effects. And in science, that is already huge. Many important things are not visible in themselves. What matters is that they modify the behavior of the world in a precise and repeatable way. Spin, therefore, forces us to make a small mental effort. It asks us to abandon part of our everyday intuition. It tells us, in substance, that the microscopic world is not a miniature version of the world you know. It is not just the same setting made smaller, it is a universe with its own rules, its own strangenesses, and its own fundamental properties. Spin is one of the most famous of these strangenesses. Spin is invisible, but it leaves very clear traces. As I said earlier, in science, this is often how we discover something. We do not directly see the object or the property, but we observe its effects. You do not see the wind itself, yet you know it is there when the leaves move. For spin, it is a bit the same. Physicists did not invent it just to make the theory prettier. They were forced to accept it because certain experiments, including the most important one we are about to see, showed behaviors that were impossible to explain otherwise. And the most important experiment I am talking about is the Stern-Gerlach experiment. The Stern-Gerlach experiment is a fundamental experiment in quantum physics, carried out in 1922. Here is the basic idea. A beam of electron is sent through a non-uniform magnetic field. It is non-uniform because, as explained in this animation by La Physique Autrement, the setup creates a stronger magnetic field near the upper tip. In the real experiment, they sent silver atoms, not electrons. Why silver atoms? Because they possess a magnetic moment. Roughly speaking, such an atom behaves a bit like a tiny magnet. And that is what we are first going to visualize, little magnets. Be careful, what I am about to say is a line of reasoning, not the truth itself. If we reason classically rather than quantum mechanically, we will say that each atom can orient its little magnet in any direction whatsoever. So in a non-uniform magnetic field, the atoms should be deflected by a variable amount. On the screen, logically, we should then observe a continuous band. If we send little magnets, we do indeed see this continuous band. Depending on the orientation of the magnet's north and south poles, the magnetic field creates a force that deflects them differently. You really have to keep in mind that the deflection of the magnet depends directly on the direction of its poles. So when electron or silver atoms are sent through this device, we observe that they are deflected like magnets. Up to that point, Stern and Gerlach expected that. But then, surprise, on the screen we see clearly that the electrons are strangely either at the top or at the bottom, but never in the middle. Instead of a continuous band, which is what we would expect from classical physics, we see two distinct spots. That means that the magnetic moment along the measure axis can take only two possible values, an orientation up and an orientation down. In other words, the component of the electron's intrinsic angular momentum along the chosen axis is quantized. In fact, this simply shows that the results of a quantum measurement are discrete. Before the measurement, we cannot describe the electron as simply having some arbitrary classical orientation. Measurement along one axis imposes precise values. This is therefore major evidence of the non-classical character of the microscopic world. That is the main conclusion of the experiment. And before continuing, I want to come back to certain points of the Stern-Gerlach experiment that will help make it easier to grasp. As I said at the start, the electrons must pass through a non-uniform field. And I am sure some people did not understand why a non-uniform field, because I did not explain it. So once again, let us imagine that an atom behaves like a tiny magnet. If the magnetic field is uniform, that means it has the same straight everywhere. It is as if your tiny magnet were immersed in a magnetic environment that is identical at every point. In that case, the field mainly tries to orient it, a bit like a compass in Earth's magnetic field. The needle turns, but it does not suddenly shoot north by sliding through the air. So the atom can rotate, but it is not globally pushed upward or downward. Now imagine that the field is stronger at the top and weaker at the bottom. Then the tiny magnet does not feel the same thing on all its parts. The field pulls strongly on one side, then on the other. The result is that a net force appears. It is this force that pushes some atoms upward and others downward, thus separating the beam into two. Since the goal of the experiment is to specially separate the atoms according to their quantum state, a force is needed to separate particles in space, and that force exists only if the field varies from one point to another. So the field must be non-uniform because only a non-uniform field can exert a net force that deflects the atoms and separates them. That's all. And another point I wanted to revisit before continuing is simply this. Why spin? Since particles do not rotate like tops, why did physicists use that word anyway? At first, the image of a rotation seemed to be the best comparison available. A particle like the electron behaves in the Stern-Gerlach experiment a bit as if it possessed a tiny internal magnet. And in the ordinary world, a charged object that spins can indeed produce a magnetic effect like the one observed. So the analogy seemed natural. If the electron acts a bit like a tiny magnet, perhaps that is because it spins on itself. On paper, the idea had a certain charm. It allowed people to relate a disturbing novelty to something familiar. But that image breaks down very quickly. First, because an electron is not a little classical ball with a well-defined surface that one could watch spinning. In quantum physics, a particle is not a miniature object that simply looks like a much smaller grain of dust. It cannot be described with the same images. Then, if we really push the idea of material rotation, we run into absurdities. To produce some of the observed effects, we would have to imagine parts of the electron spinning in a way that does not fit with our usual physics. In short, the comparison helps a bit at first, then very quickly becomes misleading. So, spin sounded cool at first, but now it is kind of a pain. And historically, Stern-Gerlach were not yet talking about spin the way we do today. But in hindsight, the experiment is interpreted as revealing the quantization of the electron spin. So this is it for the experiment. If we sum it all up in one sentence, atoms are sent through a non-uniform magnetic field, and instead of being deflected continuously, they split into two beams, which shows that certain quantum properties like spin are quantized. At this stage, we already know two things. First, spin is real, since we can measure its effects. Second, it is not an ordinary rotation, even though the word constantly pushes us to imagine it that way. But now we need to go a bit further. If spin is not the motion of a little ball spinning on itself, what are we actually supposed to understand instead? The real problem comes from the word particle. When we hear that word, we almost automatically imagine a tiny solid object. A sort of grain of matter, very small but still comparable to the objects of everyday life. Basically, a little sphere. And if we keep that image in mind, then talking about rotation seems natural. A sphere can rotate, so a particle could rotate too. Except that this image is precisely the one we need to start abandoning. In modern physics, and more precisely in quantum field theory, a fundamental particle is not described as a tiny ball with a surface, an edge, and an interior spinning in a vacuum. What we call a particle, such as an electron, is rather an excitation of a field. In other words, it is not a tiny pebble sitting in space, it is a quantized manifestation of a field that fills the universe. I know that put that way, it can sound a bit abrupt. The word field can seem abstract. And yet it is not an idea that comes out of nowhere. We already know fields in classical physics. The electric field, for example, tells you how an electric charge influences the space around it. The magnetic field does something similar for magnetic effects. In quantum field theory, this idea is pushed further. We consider that the fundamental entities of the world are fields, and that particles are packets of excitation of those fields. An electron is then an excitation of a certain field. A photon is an excitation of a well-known field, the electromagnetic field, and so on. This profoundly changes the way we think. Because if the particle is not at bottom a little material sphere, then the question, how fast does it spin on itself, already becomes much less relevant. We are trying to ask a quantum object a question designed for classical objects. That is when we begin to see why the top analogy is false. Not just in detail, but at the root. It has a shape, matter distributed through space, an axis around which it can turn. We can track every point of the top during the rotation. But for fundamental particle like the electron, that image does not work. We are not dealing with a tiny rigid body that one could film while spinning. So when physicists say that a particle has spin, they do not mean that it rotates mechanically like a tennis ball. What they mean is subtler. You have to focus here. Spin describes the way the particle quantum state behaves when a rotation is performed. And that's not at all the same thing. The distinction is essential. In one case, you imagine a material object really turning in space, and in the other, you look at how the mathematical description of that object changes when you rotate the system. So we move from a mechanical image to a transformation property. I will not lie, it is very difficult to picture this visually. We are really entering mathematical territory that becomes abstract. What you simply need to remember from what I just said is that spin does not answer the question, does the particle spin on itself? It answers the question, how does the state of this particle react if we change the orientation in space? It is not the motion of a little top, it is a very precise way of existing with respect to rotations. And this is why spin is such a deep property. It is not merely added to the particle like an accessory, it says something about the way that particle fits into the very geometry of the world. Space allows rotations, and particles do not all respond to those rotations in the same way. That part, at least, can be visualized. If we consider a 90-degree rotation, seen only from the front, the state of a Rubik's Cube does not change. For mini Lego F, it changes with each 90-degree rotation until a full turn is completed. And if we take this king of diamonds, the state is identical every 180 degrees. These three objects, therefore, do not respond in the same way to spatial rotations. And likewise, particles do not respond in the same way to rotations of space. Spin is precisely what classifies that response. From there, we can put it properly. Spin is linked to a fundamental symmetry of nature, rotational symmetry. If you rotate your experiment, or if you change reference frame, the laws of physics must preserve a certain consistency. But quantum states can transform in different ways under these rotations. And the way they transform is exactly what spin measures. So when we say that an electron has spin 1.5, we are not saying that it rotates halfway or performs some weird half rotation. It is not a speed, it is not a number of turns per second, it is not even a material rotation. It is a much more abstract, but also much more fundamental piece of information about the structure of its quantum state. In fact, the word spin remained for historical reasons, but one almost has to learn not to hear it too much in the ordinary sense. The danger is that it constantly drags us back into classical intuition. And the whole story of spin is precisely about forcing us out of that intuition. Spin is not a hidden rotation that we would eventually see if we had a powerful enough microscope. It is an irreducible quantum property linked to the way particles behave under rotations of space. In other words, if you really want to understand why spin is not a rotation, the answer is not just because it is quantum. The deeper answer is because a fundamental particle is not the kind of object that can be described as a tiny spinning ball. In quantum field theory, what is fundamental are the fields. The particles we observe are quantized excitations of those fields. And spin is part of the way those excitations exist and transform. At this stage then, we have replaced a bad image with a better idea. It may not be an easier idea to visualize, I grant you that, but it is more accurate. That's it for the video. If you want to go deeper and better understand this story of rotation and what integer and half-integer spins mean, I invite you to watch Science Click video. It goes much further into the mathematical explanation thanks to its incredible animation. My video is meant to be an introduction to understanding this complex notion. So in the comments I will post links to other interesting YouTube videos worth watching on the subject. Do not hesitate to boost the video, you need to swipe right in the comments. Do not hesitate to like, comment, subscribe and so on. Most of all, I hope you enjoyed the video. And all I have left to say is see you next time.